Hi guys, in this video we're going to talk about some different types of energy as we analyze some heating and cooling curves. So we're going to do this on some Cornell paper. Here we go. Don't forget to fill out your name and your class period and your date. Our objective is 2.3 energy in a system, and our essential question is, how does energy change when a substance is heated or cooled? So you're watching this video after you have completed the heating and cooling curve lab. And in that lab you got to look at some heating and cooling curves. And so what I'm going to do is I'm going to draw what a more complete curve looks like, because you didn't start with a really cold solid, and go all the way up to a superheated gas. But you did see the middle. So let's say that on our x-axis we'll have time, and on our y-axis we'll have temperature, and we started at some low temperature, who knows what it was, but it goes up, and then it leveled off for a little while, and then it went up again, and then it leveled off again, and then it went up some more. And maybe those weren't all parallel, except for the flat parts. The flat parts were. And so when we look at this graph, what we need to do is we need to look at the pieces individually and kind of analyze those. So I'm going to zoom in here. In this first section, there's really kind of 5 pieces. Well, that's not at all what it is. That's fine. Okay, there's really kind of 5 pieces here. 1, 2, 3, 4, and then 5. And we'll call this 1, 2, 3, 4, and 5. And when we think about what's happening to the particles, we need to think about what phase they're in, and also what those particles, how those particles are changing. Okay, so we'll start by looking at the phase. Let's pick purple. That looks good. Okay. So in part 1, it's a solid. If you think about it, there's solid, liquid, gas, and then the transition from solid to liquid, and the transition from liquid to gas. And that's what we're seeing in our graph here. So what we have is a solid, and going across from, maybe we'll call it A, B, C, D, E, and then we'll have an F over here. From A to B, then what our solid is doing is it's getting warmer. So our solid from A to B is getting warmer. Now I know it's getting warmer because temperature is on my y-axis and the line is going up. So it has to be getting warmer. So what does that mean about my particles? Well, we learned in our previous objective that temperature tells you how fast they're going, so the particles are speeding up. Now, once they get to B, once they get to this line from A to B here, so here we are, we started out cool, we're warming up, warming up, warming up, warming up, and then we get to this B spot here, we're still a solid. That whole section of part 1 is where we're solid, and our temperature is getting warmer. Left off the R, there we go. And so then we want to look at part B. Okay, so in B, what we have here is that we're going from this B to C here in part 2. Sorry, I didn't mean to call it B. Going from B to C there in that part 2, what we have is a phase change. So I'm going to write that, phase change. This was the part where our solid was beginning to melt. So we're going from a solid to a liquid. Now if you think back to our first objective in Unit 2, when we were looking at what's going on, this is called melting here. We watched that Eureka video, that really cheesy like 1970s or 1980s video about phase changes, but we saw that what's happening is that those particles, they're attracted to each other, and so they're losing attraction. So from B to C, the particles lose attractions. So those particles were stuck together in the solid, They really like each other. They just sit there and wiggle back and forth. They wiggle faster and faster going from A to B. And then once you get from B to C, they don't change speed, but they change how they're moving. Instead of just wiggling back and forth, now they're moving faster and sliding past each other. So they are breaking attractions. So I'm going to write that here. They are breaking attractions, breaking apart. So as we add energy, a note here, no temp change. How do I know there's no temperature change? Well, the line is flat. As I go from B to C, it stays right there at that same value there. Okay, so I know it's not going up anymore. My temperature has stopped changing until it's done melting. So it's all a solid at B, it's all a liquid at C, and it's changing over from liquid to solid, solid to liquid, going from B to C. So let's look at the second part. Now, the third part of our graph here, going from C all the way up to D. So now we've got something else going on here. My temperature has started changing again. So for part 3, it's going to look a lot like, whoops, wrong button, a lot like part 1, except now I have a liquid. So my liquid going from C to D is just getting warmer. Which means that my particles are speeding up again. So just looking at those two pieces right there, or three pieces right there of this graph, we can see that my particles sped up going from, my particles sped up going from A to B, then they broke apart their attractions going from B to C, and then they started speeding up again. What's happening at part 4? Well, the same thing that was happening here, so we'll describe that one the same also, except instead of melting this time, my object or my sample will be doing something a little bit different. But I ran out of room, so let's move on to the next page here. So we were looking at our graph, and we have a line that goes up a little bit and then flat and then up and then flat and then up. There are 3 ups and 2 flat parts. Flat parts. Be careful. Make sure you are looking at those the right way. So we've got the part 1 and the part 2 and the part 3 and the part 4 and the part 5. 1, 2, 3, 4, 5. And we had A, B, C, D, E, F for those boundaries there. And we talked about going from A to B and B to C and C to D already. That was our solid that melted and then a warming up liquid. And so now we're ready to look at part 4 there. Part 4, right here, is flat again. Let me zoom back in here. There we go. All right, part 4 is flat again, and that means that the temperature is not changing. This is another phase change. Phase change. This time our phase is going from a liquid to a gas. And depending on how fast that's happening, this is probably boiling. But it could also be evaporation, but it's more likely to be boiling because we're probably adding heat in a quick manner. So it's probably happening all over. So this is the boiling point. The temperature that happens is the boiling point, which I didn't mention when we were doing the freezing or the melting. This right here would be the melting point, and then we'll talk about how melting and freezing work. Also, so there's the boiling point and there's the melting point. Okay, so what's happening here again is we're breaking the attractions between those particles. Remember, in a liquid, they're kind of attracted to each other. They do some dancing, but they slide around. They stay close to each other. There's some attraction there. And then when we make it boil or turn into a gas, then we lose all those attractions. So we're chopping up the little attractions. So it's like maybe they have rubber bands connecting them, and the energy that we're putting in is going to chopping up those little rubber bands so they're not connected anymore. So, so that's part 4 there. On part 5, we've got, it's going up again. Our line is going up again, which means that our temperature is changing. So what this is now is it's our gas. And our gas is heating up, increasing in temperature. This one's really hard to see in a lab because you have to have some pretty special setup equipment to be able to see it. But what's happening here is that our particles are moving faster. Particles, speed up. So that's going from E to F in our picture. So that's what's happening there. So they're speeding up, just like they did going from A to B and from C to D in parts 1 and 3. So you can see some similarities here to these graphs about what the particles are doing, which is actually really important